Hello.
We'll be able to hear you fine. I'm so sorry. I'm sorry. They have not worked in the past. Shriram wrestles. How do I turn it?
He doesn't wear it anymore.
He doesn't wear it anymore. Because the ceiling mics are working. You are certain of this. Okay. Okay. Then I'm going to get here. Please. Good morning, everybody. So, in a fun-filled and exciting variation on CS19, this is CS19, right? Yes. Okay. So, presumably Shriram warned you all? No. Okay. So, newsflash, I am not Shriram Krishnamurthy.
No way.
Actually, my name is Tim Nelson. I'm also faculty here. I teach some other courses, including Logic for Systems, and I'm going to cover software engineering in the spring. I've been asked to stand in and give a guest lecture. Okay? So that's the deal with that. I don't know what the deal is with this. Hopefully we will get to have fun and exciting live coding with explosions and things going wrong. And until that works, I'm going to whiteboard it. Right? Like it's 1900. Okay. So, you all just, you've been talking about lists, right? I think you just did, what, quick sort on lists? Yeah. All right, so I want to talk about data definitions a little bit. All right, so if we're writing down the data definition for a list in Pirate, what does a link look like, right? It's a two-parter, but what does a link look like? Data definition for a link. Yeah?
First, which is a number, and a rest, which is a list of, a first, which is an A, and a rest, which is a list of A.
Yes. Okay, so I am going to talk about lists of numbers for now, right? But if we've got lists, we're going to have some data definition. Let's call it a num list. Right? And one of the cases is going to be, I call it a link, right? I've got a first, which is going to be a number, and in Pirate we have those. And then we've got a rest, right, which is going to be a num list. Okay, so just small aside, like Shriram, I encourage interruption with questions. So if you have a question, speak up. I have only one requirement, and the requirement is that you raise your hand first in order to avoid spoilers. Okay? Everybody cool with that? All right, so just a quick reminder of what a data definition for part of a list looks like. Today I want to start to talk to you about data structures that don't look like these linear chains of things. Right? In particular, the example that I'm going to talk through is family trees. Right? Everybody has two biological parents. We can imagine a data structure that has, instead of firsts, a name of a person, and instead of just one rest, that has both of their parents instead. Okay? Biological father and mother. Any questions? So this is a drastic deviation from the linear pattern that you saw in lists, but it's actually not going to be that different. So help me write down the link case equivalently in the family tree case. So I'm just going to say, let's call it person. Let's anthropomorphize our data. And what's going to go into a person? Sketched it a bit ago, but give me, yeah.
Root 1 and root 2.
So there's going to be some parents, parent 1 and parent 2, and we got to have some data about the person, right? So in this case, we're just going to keep their name, which I'm going to let be a string, and we're going to have parent 1, which is also a person. Up here we've got data person. And we're going to have person 2, also a person. All right, and now let's just start coding, and here is where I would be jumping onto the laptop if I could. Let's just start coding. So here's a function that we might want to write over this family tree. Let's write a function that, pardon typos since this is the whiteboard, let's write a function that counts the number of people in a tree rooted at some input person. Right? So I'm going to give you the signature of the function, and then we're going to try to write it together. All right? So I'm just going to call this one function count people. Function count people is going to take what? Going to take a person. And it's going to return a what? It had better return a number. Okay. I want you to take 30 seconds with your neighbor. Hold on to that thought. 30 seconds with your neighbor and think about how you might apply the same patterns that you would apply over lists in this case. If you see a problem with the data definition, we'll get there. Go ahead. Think about how you might apply the pattern. All right, so there are two issues in the air here. Let's focus on sort of the answer to the pattern. What kind of pattern am I going to use? I'm going to recursively descend. I'm going to match on the person, right? I'm going to have a cases statement. Right, so I'm going to cases. This is going to be cases of person. Note that we have only one case so far on P. And well, we have the lowercase person case. They've got a name, they've got parent 1, they've got parent 2. We're going to do something with that. What might we want to do? Somebody? Yeah.
Add together count people for parent 1 and for parent 2.
We're going to want to recur. But then what else do we need to do as well? Yeah.
You want to add 1?
We need to make sure this person gets counted. Very good. So, the pattern that we're going to use is count people P1 plus count people P2 plus 1. All right? Now, we've gotten this far in the programming. Some of you have been shaking your heads unhappily with me. We got this far in the programming. Can we ever actually run this function on something? What's the problem that's going to happen? Oh, well, okay. Fair enough. But the deeper problem. Go for it.
It's going to recur infinitely since there's no other definition for the person.
There's no way for this function to stop running. That's, in this case, problematic. But even more foundationally, the function will run forever, but
Your data structure isn't finite.
data structure isn't finite. I can't create an example of a family tree in Pirate to even invoke this function on. Okay? And we got this far because I said, let's just start coding. What did I not follow? I did not follow the design recipe. If I had written down examples, I would have very quickly realized that I can't write down any examples of this. Okay? So learn from my, in this case, contrived pain, not from your own pain, and follow the design recipe. Because it's only going to get easier to make this kind of mistake. All right? Questions on this point that I'm making before I get to the cool stuff? Okay, yes, we are indeed going to go and add a base case to this data. Okay. And the base case that we're going to add is, I don't know who this parent is. Okay? Now with that addition, I don't know who the parent is. Let's see if we can write down some examples. Okay. Somebody give me an example of a now finite upward family tree from somebody. Yes.
Unknown.
Ooh, unknown is an example. Okay, other examples. Yes.
Just a person with both parents as unknown.
A person with both parents is unknown. They need a name though. Give them a name. They're your person.
A.
A. Okay. Capital or lowercase?
Lowercase.
Okay, lowercase a person. And they have unknown for both parents. Also, a finite upward family tree. One more example, please. And I want to get somebody who I haven't yet called on. I mean, I can think of an example because I know the names of both of my parents. Okay. You don't have to provide the names of your parents, but an example like that. Somebody give me an example like that. Yes?
You have three people, person A, and then it links to person B who is unknown parents, and person C who is unknown parents.
Ah, okay. So, and I'm going to abbreviate this because I don't want to write too much. I'm going to have a person A, and their parents are going to be person B, unknown, person C, unknown. Did I get that right?
Two unknown parents each.
Oh, yes. Yeah, that wouldn't even parse, would it? Good. Okay, so let's draw these. Unknown is just sort of like, there are no people here in the tree. Yes?
Quick question. In this structure, can you link to the same parent from more than one node?
Can you link to the same parent from more?
So you can make a person at one level that has a parent B, and then another person C who has the same parent B but a different parent other.
If you have a means of instantiating a person and then storing a reference to that person for both parents, yes, you can. Other questions? So there are some issues with this essential data structure. This is an interesting design question, and I promise to get to some even more bizarre design questions by the end of class. Okay. Yeah?
Yeah. Oh, sorry. I mean, I was just gonna ask about inbreeding, because it's like you don't want to double count any people, if you know, right? If the family trees cross over.
If this isn't actually a tree,
right?
if it's actually what's called a directed acyclic graph, like there are some places where the lines join again,
Yeah.
our count function might have problems. And I'm going to defer that to a later class because you're going to talk about what happens when you don't have just trees in that later class. Good. Lots of design questions that come up here. Good. Let's draw these really quick so we make sure everybody has the same intuition. So what is this one going to look like? If we were going to draw a picture corresponding to this. I'm going to have A, and I don't know who the parents are, so I stop the tree there. Here, I'm going to have A still, right? And then what?
B and C.
B and C. And I'm going to stop the tree there. Okay? Good. And we could go on and we could write more interesting examples down, but let's actually finish implementing count people. We need the other case now. What are we going to do with unknown?
0.
0, because they're not a person. They're not really a person. They're a part of the people data type, but they're not really something we can count. We don't have a name. Okay? Good. Before we move on, I want to step through how this function is going to run on, say, this example. Because it is very similar and yet subtly different to what's going to happen with a list. So let's say that we call count people on this person, this third example, the person whose name is A. We're going to start here. And then what's going to happen? What function invocations are going to occur next?
People.
We're going to call count people. It better be count people. We're going to count people on B. Is that all we're going to do at this level? No, we also got to count people on C as well. So this is tier 1, this is tier 2. And then each of those is going to count people on their parents, who are in this case unknown. All right, so it's not that you have exactly one invocation. You're going to call one function with an argument at a time, but the invocation of count people on the person A has two obligations to discharge. It's got to recursively call count people twice. Yes?
What do you mean by like tiers? Because it seems like some of the sort of empty cases of the third tier will be like called on before like C, for example. Like what do you mean by like?
Depending on the model of the programming language that you are using, you could imagine different orders for these invocations to occur.
Okay.
So I'm just sort of abstracting and saying, look, this is sort of the root call. The children, one generation up, you're going to have these calls.
Okay.
2 generations up, you're going to have these calls.
Okay.
Good. Other questions? All right, so far, essentially like a list, right? But a list with 2 pieces per cell. Let's define a more interesting family tree. What about, so these family trees go upward, right? So I've got a person and they have 2 parents. That person has 2 parents. That person has 2 parents, and so on. What if we were to define family trees sort of in the style of royal genealogies, right? Where we flow downward from some historical character. Okay? So we're going to have some Genghis Khan, Alexander the Great, whomever, as a node. Or Shriram, right? The trouble with these is if you use living people, no matter how awesome they are, the downward tree isn't going to continue very far. Right? So far, far in the past, some ancestor of Shriram's. We're going to have that. And every person is going to have some children. Okay? What I want you to do is give me a couple examples of trees that look like this. And then we'll move on to the data. Well, you got to start with a person, right? Okay. Give him a name.
Henry VIII.
Henry VIII. I know I'm committing the sin of not using Roman numerals. All right, so I don't remember who all of Henry VIII's children are, but let's say that Henry VIII had some children. And let's give names to them. All right, let's say Henry VIII had 4 children. In the interest of time, let's name them A, B, C, and D. Okay? Let's say A did not have any children. That's ambiguous. Just stop there. Let's say that C didn't have any children either. Let's say that D didn't have any children. But B had children. E and F didn't have children, E didn't have children. This is the sort of tree that I'm talking about. And you can imagine maybe a forest instead of a tree where we have multiple historical figures. Maybe those trees meet at some point. Okay? So, I want to give you a minute with your neighbor to talk about what the data definition for something like this must look like. Okay? This is more complicated than the upward family tree case, and we're going to spend the rest of class talking about why. Go ahead. Oh, yeah, question? You are free to do
So it should probably be sets of groups, right? Because we don't care about the order. So just sets that, and there's no thing that can't part of our
Instead of two,
you can name them the same.
you just have children.
Yeah, because that would be our close. Because like usually,
And then you can link if you name them the same name, each of them by now. And then they get out the same name as
Hum if you need more time. Okay, so let's move on. Thoughts about what the data definition should look like. To make room for this, I'm going to wipe these out. The data definitions are going to need to look different. Ideas about what kind of data definition I might need to represent these downward family trees. Yeah?
Like data person with person being a name and a list of children, which are also people.
So I've got a people, I have a case within their person, they still get to have a name. And then what?
They have a list of persons as children.
And then they have a list of persons, which I'm just going to represent as children. All right?
And then you need some kind of unknown or no children.
And then you need some kind of unknown or no children. So I'm just going to represent this as unknown on the board for now. We will come back to that.
Oh, well, yeah.
Any additional ideas that aren't replies to the unknown point? Yes?
I mean, if you want to link like two trees, then you need eventually probably a list of parents, but I don't know if we're doing like that.
Excellent. Hold on to that. Do we need to have a list of parents? Other thoughts? Yeah.
Instead, we could define and have a person have a name, an oldest child, and a next youngest sibling.
So let's see. So would this look like person, name, oldest, and then
Oldest child and next youngest sibling.
Of the current.
of the person or of the oldest child?
Of the person.
Ah, okay. So next.
interesting.
Clever. Other thoughts? All right. As you can see, there is a significant design space here. There are a lot of different options for how to represent this data. I'm going to pick one that I think is going to take us somewhere interesting, and then we're going to loop back around. All right? Other questions or comments? Let me address one of the questions that we got earlier about unknown. If all we care about is trees like this, we don't care about being able to climb back up the tree. We care only about downward movement in the tree. Do we actually need an unknown?
No.
But now there's no base case! Where's the base case? The base case is the empty list! So a base case is not always an explicit thing in the data definition. What does it mean to have hit bottom here? It doesn't mean that this is an unknown in a list. All it means is that F has got the empty list in their children field, in this conception, in this data definition. Okay? Good. Here's where I really wish I had my laptop. Let's just charge ahead. What I want to do is take this data definition and sort of make it completely explicit. But first, yes?
They had your laptop projected.
They did. It was working for a while.
I think it's still plugged in.
Does it actually work?
It was. If we saw your
These computer things, I tell you, when they work. It seems to be... God, please don't touch anything. Okay, so what we're going to do is we're going to take these data definitions. Are you everybody able to see this? Like if I type...
Yeah.
Okay, awesome. So we're going to take this data definition and we're going to make it a little bit more explicit. Okay? Concretely, what I'm going to do is instead of like just saying this is a list of people, I'm going to unfold that into its own data definition. Because we're going to go somewhere interesting. Okay, so I'm going to have data person. I'm going to have only one case. There's going to be a name. And there's going to be a children. Right, am I getting my pirate syntax right?
Yeah.
Okay, would you tell me if I wasn't? Please say yes. Okay. And so child list is, what am I doing? Child list is going to look like an ordinary list, right? Except instead of none or nil or whatever, we're going to have no children. And it's either going to be no children or it's going to be child, which is going to contain, well, what's the first of a child list?
Person.
It's going to be a person. And the rest of a child list? It's going to be a child list. Good. Notice something interesting here. These two data definitions refer to each other. A person is always going to have a child list. And a child list, which is not no children, is always going to refer to at least one person. There's a cyclic dependency between these data types. Yes?
Why do you need to? Can't you just have children is a list of person?
I could say that children is a list of person, but then that would hide the point that I'm in the middle of making right now. I want you to see that, what's called mutual recursion between the data types. This is going to become important when we go back and try to re-implement the function we just did. Other questions or comments? All right, again, this is only one option for representing this data. There are other options, and we're going to get to that. But let's stick with this one. All right. Okay, so now we've got an example. We've got a data type that looks reasonably well-founded. Let's see what happens when we start coding. So I'm just going to abbreviate this to count, and I'm going to say, well, give me a person, and I'm going to give you a number. Right, same as we had before. Okay. Now how am I going to do this? How am I going to break it down? Different or same as before? I'm processing one of these data types. It's got cases, even if it's only one case. Everybody okay with me using cases? Cool, okay. This is the person case of T, and we're only going to have one case. And well, what is it? We've got a person, the person has got a name, and it's got some children, and we're going to go on from there. Did I misspell something? This looks okay. All right, so, well, clearly the same pattern is the right thing to do. We know how to break down something recursive like this. I want you to take a minute.
We can.
What's going to go wrong? Somebody who I haven't called on yet today. Something's going to go terribly wrong. Yes?
CS is not a person yet.
CS is not a person. CS is a child list. If I try running this, I would get an error. So this, I can't just plug in the pattern. There's not one recursive pattern. I have to figure out what the right pattern is for this set of data types. Yes?
Let's do another case of statement.
Okay. So what's this going to be a case on?
This is going to be a case of on child list of CS.
On child list of CS. Okay. Anybody have any thoughts on where I go from here? sorry? I'm not the best pirate, so if I've made a mistake here, let me know. Yes?
No children, you just return 1.
So no children. I need the... No children, just return 1. And then other case child. So I've got some child and I've got rest. And now what am I going to do? In the back, yes.
You can run into the same issue because you still can't count the rest.
Ah. Everybody see this excellent point? I'm going to run into the same issue. Because how do I process this rest? Well, I have a third cases statement. And then that's going to have a rest. And then I'm going to have a fourth cases statement. And then that one's going to have a rest. And so on and so on. I need a way of handling this mutual recursion. I need a way of saying, well, I have broken apart this person, metaphorically speaking. I've got their list of children, and now I need a separate function to process this list of children, right? A nice design pattern that you will find yourself following is if you have multiple data types, it is often nice to have separate functions to handle those data types. Because here's what we're going to get. If we don't have this extra cases, right, I'm just going to say, well, I want you to count the child list, CS, and then add what? 1 for this person. How do I count a list? Count function says, that's not my problem. That's count lists' problem. You go write count lists now. Okay? Separation of concerns makes programming much, much easier. Okay. Unfortunately, now we have to write another function. What's it going to take? A child list. What's it going to return? Going to give you a number. All right. We have a data type. It's got 2 cases. We're going to use cases. Cases of child list. Indeed, it's going to look very like what we had before, and I helpfully erased. Cases child list of C. We're going to have 2 bars and an end. First bar, no children. How many people?
0.
There are no children to count. What if we have a child? Okay, so let's try 1 plus count list of rest, right?
Yeah, so it's
Okay, if you see the problem, don't... Spoilers. No spoilers. Okay, this is the natural thing to try first. It's the same pattern as before. You just add 1 to recur on the list. Right? It is the same pattern as before. And yes, something is going to go wrong. We'll get to it. But this runs, right? And I could write down an example. So let's just say example 1 is going to be a person. I'm not going to do that whole tree, but let's just name him Henry 8. And Henry 8 is going to have 1 child. And what should we name the child? Let's give them a real name.
Elizabeth the First. Does it need to be a person? It's Elizabeth the First.
Okay, let's not give her a number this time. And
It needs to be a person.
She wasn't first then, she was just Elizabeth.
okay, so there are no more children after Elizabeth I, and
She needs to be a person.
she needs to be a person, not a string. And let's say she has no children. Right? And it's always problematic to represent these sorts of examples nicely, textually. But this is a 2-node tree. Yes?
Can you just like enter a bunch of times and then scroll up a little bit?
Can I enter? Oh, you're having... Oh, yes, of course. Good? Okay. This is exactly the sort of thing you should interrupt me with. Good. Okay. And I can run this. assuming I haven't made any terrible mistakes, I should be able to call count on E1. What do we expect? Everything is fine. We can all go for ice cream, you know, our code is perfect. Here's what I want you to do. I want you to spend a couple minutes with your partner working out a test case that will cause this function to fail. And I think it's all on the screen. Yes. Okay, take 2 minutes. Take your time. Give me a test case where this goes wrong.
Like for each person, it's supposed to go back. Yeah, it's supposed to go back to which is really weird. Just like it's really cool. It's really cool. It seems like it should explode. It will explode if you don't just true. If you don't take care of food, you do it.
Small editorial remark. You are free to assume that your test case is a real tree. I'm not playing any tricks on you with shared ancestors or anything like that. It's just a tree. Go ahead, keep going.
So third generation, it wouldn't count in order to
Who's our resident?
But there's other
Oh my god. That's gonna be he's gonna so that's gonna be like this.
Hum if you need more time. I don't hear any humming. Does anybody need more time? Hum, hum, hum. Oh, you're talking, not humming. Okay, that means we're done. Okay, so test case that causes this function to fail. Who's got one? Among the people who I have yet to call on today. Yes.
If you just give Elizabeth a child, it will break.
If I just give Elizabeth a child, it will break. So let's try this. Okay, so I'm taking away no children here, and I'm giving Elizabeth a child. And what's the syntax for this? Well, I create a person, and then they have no children. And what should we name Elizabeth's child as the...
James. I have no clue if that's a
James. Well, we didn't say which Elizabeth. So, okay, and James has no children. Right? Does that look right? Okay. So, we're going to rerun this. And how many people are we expecting?
We're expecting. Well, we should.
We better get 3. We only get 2. Okay. This looks great to me. This is a nice simple pattern, 1 plus count list of rest. What went wrong?
Skipping the child.
Okay, so there's something going on with me skipping a child. Somebody help me with a little more focused information. Yes, in the back.
You're only counting like how many people are in like the first child list.
I'm only counting the first child list. I have a data type. That is mutually recursive, right? People refer to child lists refer to people, those people themselves refer to child lists, and so on. It is a very, very suspicious thing that in CountList, I invoke CountList. I'm getting that horizontal structure. I'm getting all the siblings. But I am never, ever invoking count. I'm never saying, well, the child in the list, they're a person. They may themselves have descendants who need counting. Okay? So a good pattern to watch for is if you have mutually recursive data, like we have with person and child list, you should see invocations for the appropriate data types. This is another reason why it's useful to split up functions for each data type you've got. So what do I need here? What's broken? Is count list broken?
Well, yes.
Is this invocation of count list on line 22 wrong? Okay. Is it +1 that's wrong?
Yes.
What should I replace that 1 with? Spoilers! Take 15 seconds with your neighbor. I want everybody to understand what's wrong here and how to fix it.
I like that. Count C. Count C dot first.
Alright, hum if you need more time. I hear no humming, we're done. Okay, somebody I haven't called on before. Help. Yes?
You would put count of C2.
Why does that fix it? Somebody I haven't called on before. I think there was a hand. Yes, why does that fix it?
Because then it'll go back to the count function all again, so you can get the kids of C2.
Yeah. So I will have this function both crawl deeper, get that person, call count on them, maybe handle their children, and handle all the siblings of the current child under consideration. I've got to do both of those things. I have to recur on both those data types. Excellent. Okay, and now, but wait, don't just take my word for it. What should I do? I should run it. And I could write a nice pirate statement, but I'm not doing that. Okay, so I claim this is good enough for now. You would certainly want to test on more elaborate data. For instance, I might have just broken the ability to handle more than one sibling. Do we have a test that's going to handle more than one sibling yet? No, we do not. And we don't have a test for things that are like more base casey and so on. So if we were not running out of time, we would test a couple more things, and you would hopefully believe me a bit more strongly. Any questions about this before I move on? Yes?
The order of count and count list on 22, does it changes something if you flip them, right?
But what?
In the order of function calls, like it either goes across the siblings or down.
This is a great, okay. So let me know if this is the question. If I were to replace this expression with instead this expression, what changes? Am I right?
Yes, that's
Okay. I have two levels of answer for you. At the level of CS19 as of February 20th, February, what month is it? September. As of September 20th, these are just algebraic expressions, and addition is commutative. So nothing changes. As you progress in your CS careers, there are subtleties that happen, right? For instance, if somehow every time I called count list, I played a wave file of a cat meowing, and every time I called count, I played a wave file of a dog barking, you would notice probably a change in the order of meows and barks. But at the moment, these are algebraic expressions, and we are free to permute them as we see fit. Answer your question?
Yeah.
Cool. Okay. In the last 4 minutes, I want to come back to these other design choices. Okay? Why might it be good to have an unknown case in person? Why might we need that? What could we add to make that necessary? Somebody I haven't called on. I don't know all your faces yet. Sorry. Yeah.
Like, if you know they have children, but you don't know who they are, you can give them unknown children.
So you could give them unknown children, but doesn't... I see. So you're pointing out a semantic difference between unknown and no children. I'm going to completely sidestep that interesting philosophical point and pretend that they're exactly the same. There's like a sort of programming reason that we might want to add unknown because we're adding something else. What else might we add?
If we add a parent.
Spoilers. Thoughts? If we add what? Yes?
So if we do add parents, then we would need unknown, which we saw from the very first proof that we made.
If we care to know from some node what its parents are, who its parents are, and, in the interest of time I'm going to speed through this, and we choose to store that parental information in a P1 and P2, like we did in the upward family tree example. Now we need some way to represent I don't know who the parent is. And then we need an unknown. Okay, so if I were to write something like this. Oh, that's funny. There we go. I promise to finish in 2 minutes. If we do something like this, where I've got P1 and P2, so that I can go up the tree as well as down. Now I need something to put into the P1 and P2 when the tree doesn't go up anymore. Otherwise we're going to end up with the same problem we were at 5 minutes into class. Everybody see that? Questions? Okay. There's another way that we could store parental information. What is that way? Yes?
A person list or like a parent list?
I could, instead of having P1 and P2, I might choose to have some parent list. I mean, sure, I would go in and I would rename child list to person list. But same idea, right? I'm going to store a list of parents. Then I'm not going to need unknown anymore, because my base case, I don't know, is going to be either one parent in the list or no parents in the list. However, what is something that could go wrong in the representation if I use a list to store parents instead of P1 and P2? Yes?
There could be more than 2 parents.
I could have 17 parents in parent list, and the data representation will allow it. Okay? So if I were to choose to implement this 2-directional tree, I would probably use P1, P2, and unknown. But there is a whole space of design choices with their upsides and their downsides. Okay? And that's the sense that I want you to go away with. At this point, there start to be complexities. All right? I'll stick around for a few minutes if you have questions. Have a great day.
That's how biology works.
So if we did use a list for parents, would we have to basically have a third counting method to count upwards? Because if we use the same counting method, then once we go up, it's
Depends on what you want. If you're saying, I want to compute the number of people in the downward tree rooted at
meeting,
you don't
and
need
they're
to have the part
then that's a problem. If I'm around, yeah,
but
if I'm around.
if you want to search in both directions, you absolutely
Given what at least we know so far and playwright description, it's possible to
I need like people behind me.
the new one. Like the stairs. You have to like.
I need an unknown.
Yes. Okay.
Let's
check. Is there a way to like? I know you can like mutate a variable, but can you mutate a like reference?
I have no idea at this point what mutation even is.
Okay.
Thank you.
Thank you. Hey.
I'm Daniel. Nice to meet you.
Nice to meet you too. All right. Thank you for fixing that.
Sorry about all that.
It's fixed.
Is there a way to like count like every person in a family tree like with?
Oh, in given what I just showed?
Yeah.
Yes. So Shriram is going to be talking about exploring sort of arbitrary structures like this that are called graphs.
Because,
In a couple weeks. But so trees are graphs, but a graph is more general. For instance, a graph might have cycles in it, right? So think about the graph induced by all the cities in Rhode Island and the roads between them, right? If your search process is sort of a blind, like you're just crawling forward and counting, crawling forward and counting, crawling forward and counting, you're going to hit cycles. There's going to be loops, and you'll never turn.
I think my question is like, if we have a list of parents and the parents have children, because they're people.
You can run into the problem again. Exactly. Absolutely.
So, but there's a way around that.
There's a way around that. Shriram's going to talk about it in not too much longer. Okay. Hello. Hello. Okay. Be right back. It's all good. It is stick around for 2 minutes and I'll be done.
This time instead of just like a one paragraph.